We are going to be starting chapter 9.2 right now, and I have skipped over 9.1, but I will be reviewing some things from 9.1 in this 9.2 section. But the approach that we're going to be doing for chapter 9, 10, and 11 is a lot like what we did for chapters 7 and 8, where chapter 9 and 10 are review. We're going to be looking over trig, just reviewing some of the old things that we've learned in the past about trigonometry, which is the study of really triangles, and specifically right triangles, and studying about angles and side-to-side ratios. But we're going to be looking over those and discussing those, and then what eventually we're going to lead to is how to differentiate and integrate these different trig functions that we've learned about. So it's important that we are going to be reviewing these things, as you can see down here. Please do take a while to look over that, but otherwise we're going to get going. So first things to look over is what is a radian. So radians, I like to think of radians as a radii or a radius. And keep in mind that we have these circles here, and so here's my circle. And what we have is this length, this certain radius length. And what we can do is use that length to kind of measure the arc lengths around our circle, because there's certain arc lengths that when you open up to that arc length to form that arc length on that circle, what we've done is we're going to be looking and examining this arc length with respect to the sides of your radius. Okay, so I mean, how many radiuses is that? So how many radians is that, is the correct version kind of what we're looking at. How many radians are there around an entire unit or an entire circle? Well, how many radians is that? There are, in case you don't know, 2 pi radiuses, or in other words 2 pi radians that would complete a circle. If you looked at something maybe right about here, I would say right there, that's about 1 radian, because that would be about the length of a radius right there, 1 radian right there. This would be about 2 radians, because that's about the length of my radius. This is about 3 radians, and this is a little bit more of a radius, or of a radian. So that right there is about 3.14 radians. So pi radians is half the circle. All the way around would have been 2 pi radians. So 2 pi radiuses. So that's all that information right there. One other kind of key thing is that you can convert between degrees and radians. So of course we have these degrees that would also be a measurement of an angle, and then we now are also looking at these radians, which are another way of measuring an angle by the arc length. So keep in mind that there are 2 pi radians through a whole circle, and then 360 degrees in a whole circle. So what we can do is set up a proportion like that. So let's say that I knew that I had 30 degrees, and I wanted to figure out what is the radian measurement of that angle. Well, you can go ahead and put that out of 360, set that equal to, I'm not sure how many radians, so I'm going to put in a variable there, but that's going to be completely out of 2 pi. Alright, so there's my proportion, and this is just cross multiplication at that point. I would take 2 pi times 30 degrees all over 360 degrees. These degrees are going to cancel each other out. So are these tens. Okay, and then I'm going to go ahead and multiply my 3 and 2 to get 6 pi over 36. And what we're going to get is pi sixths. So that's just kind of a quick review on how we can convert between radians and degrees. Set up proportions. Also, if you started with pi over 6, you would just have pi over 6 over 2 pi is equal to d over 360. Same thing, you would use cross multiplication. So that brings me to my unit circle. So hopefully this is going to become familiar. I do have printouts of these, but here is that unit circle. Here is that pi sixths. Think about it like this. Pi is once again about 3.14 divided by 6. That would be about 0.5. So we're saying that this length right here is about 1/2, a little less, a little more than 0.5 or half of my radius. So that's kind of, you can kind of even visually see that. There is half of a radius, and yeah, that is about 1/2 of a radius, or pi 6 radians. That is also corresponding with 30 degrees. Any one of these you could convert pi fourths into 45 degrees. All of these around the circle you could do that too. We're going to get into these here in a little bit. So there is the unit circle, a good old friend of ours. Another thing to look at are standard form angles and reference angles. Standard form angles are angles that open counterclockwise from the positive x-axis. So what I want you to see here is this right here is going to be the standard form angle. That's about a 45-degree angle, we'll say. So 45 degrees is what we're looking at there. So if your calculator is going to be calculating, for example, sine of 45 or cosine of 45, your calculator will do those for you. And what they're doing is going to be calculating what is the horizontal for cosine, and then the vertical components or aspects of this 45-degree angle. It's going to be calculating basically a triangle, the side-to-side ratios of a triangle for you when it's doing cosine and sine and tangent and whatever. But what you need to realize is that it's going to be calculating those horizontal and vertical components when opening up like this. Okay, so same thing for an angle like that. We're going to be figuring out what are the horizontal and vertical components to get there. But I mean, this is looking something like a 135-degree angle, because again, your calculator, when you put in 135 into your calculator, it will be visualizing. Think of it like getting into your calculator's brain. This is 135 to your calculator. Okay, it's always an angle that opens up from the x-axis. These things we'll kind of get into, but a reference angle is an acute angle formed by the terminal side and the horizontal axes. So we'll get into that here in a little bit. SOHCAHTOA. I'm not going to go into this a whole lot. SOHCAHTOA is going to be, if we're on the unit circle, it's going to be the opposite over hypotenuse, but also it's going to be just y over 1. Or if we're not on the unit circle, it's going to be your y. Sine is always going to go with the vertical movement on when you're on the standard form angles on the unit circle or on the coordinate grid. Y over hypotenuse, whatever that may be. Cosine is going to be always associated with the horizontal movement on the coordinate grid. So once again, if we're looking at standard angles, so cosine is always going to be the x values. 1 for the hypotenuse if we're on the unit circle, otherwise it's just x over whatever the hypotenuse is. And then tangent is going to be just y over x, or in other words, opposite over adjacent. Quick review too on the side lengths of this should be of a 30, 60, 90 triangle. So this right here, we're going to have a 30 degree. These are right triangles that I'm going to be using. And then we have a 60 degree. Here's a 45, and then a 45, 90. What I just want you to know is there's proofs of why this occurs, but if we're on the unit circle, the most basic unit circle, we're going to have a radius of 1. Okay, so you'll see these triangles a lot, or I'll be using them a lot anyway as I go through some of these problems. Here what we're going to have is that longer side of that 30, 60, 90 triangle is going to be the square root of 3 over 2, and then the shorter side is going to be 1/2. Alright, for a 45, 45, 90, we have the square root of 2 over 2 is the one of the side lengths, and then of course this is an isosceles triangle, so we're going to have the square root of 2 over 2, and then the hypotenuse, which is the side opposite from the right angle, is always 1. So when I look up here, That's why you're going to be seeing these particular numbers, because all of these key points on the unit circle are formed by these special two triangles. So here is my 30, 60, 90 triangle that we just showed. Longer side is going to be the square root of 3 over 2, and then that shorter side is 1/2. So there's that triangle. Here is that 45, 45, 90 triangle that I just showed you, and what you'll see is we have this horizontal movement and then this vertical movement to get to that point. And keep in mind, this unit circle is on the XY axes. And right here, this is that point. I mean, if we were looking at a bigger version of our coordinate plane, we have a really itty bitty little unit circle here. That's what we're looking at right here. So this is the point 1, 0. That's right there. That's what this is right here. And so we have to understand that if you did calculate what is the square root of 2 over 2, if we did calculate the square root of 2 over 2, what we're going to get is that point, oh gosh, I don't even remember, 0.86, I think. But anyway, when you do calculate that out, it's not even all the way over 1 and up 1. Okay, so we're not even making it to the 1 and 1 mark. So that's why you're going to get these kind of decimal answers here. Okay, if I were to take this and I can flip this. Okay, so here once again we have that same 30, 60, 90, and there's that shorter side. There's that longer side, so that's going to be why we go over horizontally 1/2 and up the square root of 3 over 2. And then this will be rotated, flipped in various manners. Whoops. But what you can go over on the other side, that's where we're going to get some negative and positive values, because this is something that we had to work horizontally for, and we had to go backwards from the 0 or from the origin. So this is going to be negative 1/2 and then the square root of 3 over 2.